Hello everyone, my name is Mikita, and in this video I want to share my scientific results of solving the problem of bearing foul detection by using autoencoder convolutional neural network. On this slide, you can see the raw vibration data provided and the data processed with the Savitsky-Golay filter and minimax normalization. The purpose of processing the vibration data is to highlight its class features more clearly to improve the ability of the AECNN model to recognize the detected classes. The parameters of the Savitsky-Golay filter was selected experimentally and defined as window length equal to 24 and polynomial coefficients equal to 13. Minimax normalization parameter were chosen as a lower limit equal to minus 0.3 and upper limit equals to 0.3. These values were selected taking into account that after normalization of healthy samples and normalization of faulty samples based on calculated metrics of healthy samples, the maximum model values of faulty samples will not exceed the range from -1 to 1 for promoting AECNN model high performance. Let's take a look and analyze the architecture of constructed AECNN model. The architecture was selected using the tree structured Parsons estimator hyperparameter selection method. For the architecture, the hyperparameters of the number of input and output filters for each convolution stage were selected. In the AECNN model, increasing the number of filters at each successive stage of encoder convolution allows the model to learn increasingly complex features, ranging from edges or simple patterns to more abstract representations. In contrast, in a decoder, reducing the number of filters in each stage simplifies and reconstructs the learned features back into the original data form. The incremental reduction efficiently reverses the abstraction process by helping to restore a version of the input data based on encoded features, resulting in efficient data recovery with minimal loss. The data provided from the study amount to 1,558 samples, each of which has 93,752 values. The data are divided into 865 healthy samples and 293 faulty samples. Based on zero-shot learning principle, 70% of the healthy data are 605 samples used for the training process. The other 30% of the healthy data are 260 samples used for the validation process. All 293 faulty samples are used for the testing process. Based on the periodicity of the characteristics of healthy and faulty samples, it was decided to reduce the data to the first 1,500 values for each sample in order to optimize the duration of data processing by the AECNN model. For the simultaneous processing of samples by the AECNN model, the batch size of 16 samples is determined. On this slide, you can see a table describing the process of training and validating the AECNN model on 18 epochs. The training and validation doses have satisfactory low values and gradually decrease during the epochs, which indicates the successful effective training of the AECNN model. You can also see the indicator of the faulty threshold, which is defined as the maximum validation error and has a lower value than the average test error of faulty data, which proves that the classification method proposed in this study works in practice. Why this happens is described on the next slide. In the results, it can be seen that the AECNN model restores healthy vibration samples with satisfactory accuracy, restoring the main parts of vibration data, while in faulty vibration samples, the model restores only those parts that resemble healthy signs without characteristic faulty pulses. This feature of the model enables binary classification of bearings. More details on the next slide. Here you can see a table of validation and test errors, where each value is the average error of 16 samples according to the selected batch size. On the last line, average values are calculated from the validation and test columns respectively. For all the values of the two columns, there is a clear difference between the errors, which explains the fact that the faulty samples are restored by the AECNN model without faulty features and therefore have a much larger error than the healthy samples that the AECNN model is trained to reproduce. Binary classification is implemented precisely according to this feature. In conclusion, it can be stated that the AECNN model copes well with the detection of bearing faults. It should be noted that if the vibration of the faulty samples are very similar to the vibration of the healthy samples and have barely noticeable signs of the fault, the AECNN model constructed in this study is likely to be much more difficult to track the characteristics of faulty samples and distinguish them from healthy samples by a slight difference in class features. But in general, the task of detecting the fault of the variance in the provided data set by the research was successfully solved. Слава Україні!